Okay, so what I would like to show today is CastNet, and we would like to start with a company introduction. Then I would say some words about CastNet, about the history, the workflow in CastNet, meshing and OpenFOAM capabilities. Most of the time we will spend with some demos where we demonstrate how to use CastNet with simpleFoam, and another case with Conjugate heat transfer multi-region foam. And finally, I would like to explain our testing options and the prices of our system. So short introduction of our company. So my background is that I studied process engineering at the University of Aachen. Then I made my PhD in Bremen in the field of metal melt atomization. Then I worked 4 years at Brown in the metal product development. And since 2002, I provide services for CFD, finite element analysis, and fluid structure interactions. So my coworker Martin, on the other side, has a background in computer science. He studied at the university in Hagen. He's now 10 years with me here, and before he developed flow solver for finite element methods for plastic applications. So as he has a background in computer science, he is more responsible for the programming stuff here, for automation, scripting, and customization. And Martin is also here in the webinar. So if you have questions, I suggested to write them directly in the chat, and Martin will try to answer them during the webinar. But if we don't manage to answer all your questions, don't worry, we will come back to you and answer the questions. Okay, so what we do in the engineering stuff is that we provide services. We have some special fields with OpenFOAM where we work, and these are in particular particle flows like sprays, evaporating particles, or filter applications. On the other side, we work in the field of other multi-phase problems like volume of fluid applications. We work a lot in the field of moving grid applications like filling processes or injection processes, fluid structure interactions like membrane pumps or hydro mounts. And also we have many problems in the field of heat transfer analysis like conjugate heat transfer or in combination with thermal stresses. Then we do also software development. We started here with our GUI CastNet. This is a pre-processing system for OpenFOAM. And meanwhile, we do also a lot of OpenFOAM extensions. We started here with a tool for filtrations, and our last tool that we developed is a transition model for volume of fluid to Lagrangian particles, for example, to model atomization processes. But for today, we will focus here on CastNet, our pre-processing system for OpenFOAM. So when we started here with CastNet, we've started in 2009, and at this time in OpenFOAM, we had found only very restrictive options for meshing. Only block mesh exists at this time. Even snippy hex mesh didn't exist. And most of the industrial users translated their meshes from other mesh systems. For example, they used fluent mesh to foam. And to bring OpenFOAM into companies, we found that it's very important here to have an own solution for CAD-based mesh setup and simplifying the setup for OpenFOAM in general. So this GUI has been inspired by other commercial CFD tools we worked so far. And the goal was here to allow a reliable CAD import and meshing. And for this, we found a cooperation with Symmetrics because we didn't want to develop all this meshing stuff and CAD import ourselves. And here we licensed a base system from a company in the United States, which is called Symmetrics, who provides CAD import and meshing technologies for own solvers. And what we did here is that we added here the export for OpenFOAM and also for Calculix in this environment. So also, as we use here, our base system is here a commercial system. Of course, our system can't be open source and we can't provide this for free, but we think that it's quite cost effective. So from our initial development, so in 2009, where we started, we had the first industrial users. And in 2010, we also presented this at different OpenFOAM workshops, for example, in Gothenburg, where we presented CastNet with abstract modeling, which is a technique to do automation very fast and easy. Then in Penn State University in 2011 and in 2012 in Darmstadt, we showed the cooperation with BlueCFD, where we demonstrated the usage of OpenFOAM on Windows with BlueCFD. After this time, we have been on various OpenFOAM conferences from ICON or ESI in Berlin, Stuttgart, and Duisburg, where we presented our GUI. In 2015, we added the support of Calculix. This is an open source finite element solver, and added also some coupling options to OpenFOAM for this. And in 2021, we used coupling. We added the coupling with Precise to do fully FSI coupling in our GUI. The last development that we did here was last year, where we also extended the support for BlueCFD, in particular for BlueCFD 2024, which is based on OpenFOAM 12. And also on Windows, we now support the ESI versions for OpenFOAM, and I will show this also in the demonstration. Okay, the general workflow with CastNet looks like this. As we use here the symmetrics technology, we work almost with CAD kernel input. We can import parasolid models, which come typically from CAD models, CAD systems like NX, SolidWorks, Solid Edge, ACES models, which come typically from Inventor, SpaceClaim, TurboCAD, or some others, Granite, which is a CAD kernel for Pro-E or Creo. For CATIA, we have a gap at the moment. Here we recommend to use to work with SpaceClaim, and we can also import discrete data like STL or Nastran files for a discrete model setup. With this CAD kernel-based models, which is always also a high quality CAD import, because we don't have to use here translators, for example, to use IGES or other files. We go into our GUI, where we can use a hybrid meshing or snappy hex mesh. I will also show this later in more detail. From here, we do the meshing and define the OpenFOAM settings. And after this, we can export the case to different OpenFOAM version. On Linux, we support the typical ESI versions or the versions from the OpenFOAM Foundation. And also on Windows, we support here BlueCFD, the ESI ports of OpenFOAM or Windows subsystem. And the monitoring can be always done here with RunGui. On the structural side, we also support here second order elements, which are quite important for finite element analysis. And also we use here Calculix as solver with a standard solver from Linux, or as Windows port when the analysis should be done on Windows. On Linux, we have here the coupling between OpenFOAM and Calculix directly for full coupled FSI analysis. And when the case is defined here in the GUI, in particular for OpenFOAM, then we can decide where we would like to run the case. We can run this either on our local Windows system, we can run this on a Linux machine or in a cluster, or we can move the complete case and run this in the cloud. For post-processing, of course, we recommend to use your ParaView as post-processor for OpenFOAM, and also for Calculix, we have an own translator to translate the data from Calculix into the ParaView format. And this allows, for example, to do the post-processing for FSI data directly in one post-processor with the same model. This is basically how our GUI looks like. So you can import here such a CAD assembly and then define your mesh settings and your analysis setting. And our task is basically that you define here that you can pick, for example, such a phase, for example, for the boundary condition, define your properties here, for example, a velocity and, for example, the turbulence properties. And our task is basically to translate this into the OpenFOAM file format, for example, example, here a surface normal fixed value for the velocity or the turbulence settings here, for example, in the K file or in the omega file, whatever has been selected here. On the meshing side, we have on the one side here the mesh capabilities from Symmetrix. Symmetrix is a typical hybrid meshing approach where we first mesh here all surfaces and then the mesh and then the internal mesh is generated. So here, when we import a CAD geometry, we internally create so-called non-manifold models, which allows us, for example, to access to different regions here in our model. We can use here a hybrid meshing with extrude regions. So in this case, we have here, for example, an extrude region, and here we have a hex core meshing. And this hybrid meshing approach allows also to generate very reliable and very good boundary layers. On the other side, we support here Snappy Hex Mesh. Snappy Hex Mesh is the mesher you probably know when you work already with OpenFOAM. The advantage here is that we can pick, for example, such a face and define, for example, local refinements on particular faces. We can pick here edges and do local refinements here on edges. And all these data are entered here in the Snappy Hex Mesh dictionary. And this makes the setup also for Snappy Hex Mesh easier if you would like to use Snappy Hex Mesh. The meshing is done externally in this case. So here we use a hexahedral dominant polyhedral meshing, and we recommend to use Snappy Hex Mesh, for example, if you have no fluid domain and the fluid domain has been found, for example, if you use as input just a solid model, or if you have very bad CAD quality, then the Snappy Hex Mesh approach is very robust here to generate here good meshes. Also, Snappy Hex Mesh works very well for adaptive mesh refinement. We use the Snappy Hex Mesh approach a lot, for example, in our optimization problems, where we use volume of fluid method and also do some adaptive mesh refinement. And this works very well in Snappy Hex Mesh. But on the other side, as you probably know, is that the boundary layer meshing Snappy Hex Mesh is quite challenging here to realize here very good boundary layers. And on the other side, the edge snapping can also be quite challenging in some situations. So we think in combination with these two meshing approaches that we have here in our GUI, we can cover a very broad range of CFD applications. So if you need, for example, very good boundary layer meshing, you can use the hybrid meshing. If you don't need good boundary layer meshing, but if you would like to use, for example, adaptive mesh refinement, then Snappy Hex Mesh approach might be an option also in CastNet. Okay, on the other side, we have a lot of functionality that we support here in OpenFOAM. We support most of the incompressible solvers here in OpenFOAM. Some of them didn't exist anymore, but in some older versions, they still are available. Typically are here simpleFoam, the steady state solver, or pimpleFoam, the transient solver. Then we have a number of compressible solvers we support, for example, row simpleFoam, row pimpleFoam, and also sonic foam if you have transonic flows. We support a lot of heat transfer solvers, the typical buoyant solvers, the conjugate heat transfer solvers. And on the multi-phase side, we support here, for example, interfoam, interdyne foam, compressible interfoam, drift flux foam, and also the Euler approaches like two-phase Euler foam. The basic solvers, typically Laplacian foam, Lagrangian solvers, uncoupled solvers, or also the coupled solvers like simping reacting partial foam or LTS reacting partial foam, and also combustion solvers like reacting foam, LTS reacting foam, and yeah, so some other. Okay. Besides this, we have a lot of functionality that we support. We support the conjugate heat transfer, radiation problems, heat sources, heat exchangers, many multi-phase functionality like volume of fluid, Euler, particle transport, volume zones, phase zone. I don't want to read this here completely, but there are really a lot of functionality that is supported here. But as you probably know, that the setup in OpenFOAM can be quite hard, in particular because you have here a certain kind of OpenFOAM structure, which is given by the OpenFOAM solvers, and the definitions in the solvers can be quite different. For example, in simpleFoam, you use here a pressure divided through the density. In row simpleFoam, you use here typically absolute pressure. And we try to overcome these different settings in the different solvers by so-called templates. Here's these templates. We provide here a high number of templates for each solver, which use already the predefined settings here. And for example, for the properties, for the pressure, if you use a pimple solver, for example, we have typically automatic time schemes here. And also for the output, if you use a steady state solver, you typically don't need so much output in comparison to a transient solver. On the other side, we also support the interactions with Calculix as structural solver. So, for example, if you do a conjugate heat transfer analysis in OpenFOAM with different regions, here, for example, here we have a fluid domain and a number of solid domains, and this is and we would like to translate the results from the fluid domain and the solid domains, in particular the temperature, and would like to do a thermal stress analysis. We can do this directly in our GUI, and then we use these loads, these temperature distribution in our solids here as input for the stress simulation here in Calculix. So this allows us to do analysis of thermal stress simulations, and this works quite well and is quite easy with our GUI here available. When you run the case, we have a monitoring tool, which is our RunGui, which where you can see, for example, residuals, and where you have many options here to manipulate the case. You can change here the schemes during runtime. You can stop the case or do some changes here directly in the GUI, and you don't have to add these directly here, for example, in an editor, and maybe the solver crashes because something is written in the wrong way. Also, in OpenFOAM, as you probably know, that the major results, only the important results are exported here. And if you are interested in some additional results, for example, if you do a heat transfer analysis, and if you're interested in the wall heat flux, you have to call this with a function object in OpenFOAM. And also this is integrated in our GUI, so you can use here, for example, wall heat flux, click on it, and then you get the heat fluxes in your as results in your case, and you can look at them here in ParaView. Okay, this is the short introduction of our GUI, and now I would like to start with the demo here. So here I start CastNet and import a geometry. When I import here a geometry, I use here such a model, which is an assembly model here. And typically, when we start here CastNet, we have here a number of different settings, and we work here from the left to the right. So here we are in the display tab, and then we can do here some changes with display. So, for example, we can check here how many regions has our model, and we see here that we have a CAD assembly which consists of different parts, and these are translated here into our different parts here in CastNet. In the modeling tab, we can add here geometry, or we can do here geometry manipulations. In prepare, we can clean the model. If we have slip-up faces, we can remove them. Discrete will become active when we work here with discrete models, where we can do a discrete manipulations on our discrete model. In the meshing tab, we define our meshing, and in the analysis tab, we do the setup here for our solver, in particular OpenFOAM. So I go back here to the display tab, and also what we see here is that we have different filters where when we, for example, when we would like to pick a face, we can pick here on this face filters. When we go here, for example, to region, we can pick here such a region and do it like this. So what we have here as a model is a so-called assembly model. And in this case, we have here a number of parts. We see this here in our model list. And at the moment, these parts are not connected here to each other. So when we hide, for example, such a face, and we look here at this face, for example, and we hide this face again, there's still another face. So we don't have a consistent transition here in our CAD model, because we have a different part, and each part has a specific face at the interface here. So this is typically not what we would like to have in a CFD analysis. We would like to have here regions, but only one interface in the sharing parts. And this is something that we can do here quite easily directly. We can do here, go here to model, make model, take the complete model, click on this, and then click apply. And then we get a new window here. And now we see here, so when I compare this with the original case, I can see here that all the parts that I have here are translated into regions. And this is a model I have to work with when I do CFD analysis. I can also do this automatically when I only work with OpenFOAM as solver. I can go here, for example, to preferences and here to general, and can say immediately create a non-manifold model from native assembly. Then I get automatically here these kind of region models in my GUI. And the difference now is that I have only one face between these different parts, but I still have these region information available, so I can use this, for example, for the meshing, or I can use this in OpenFOAM if I would like to do a multi-region model. For example, if I would like to do multiple reference frame analysis or conjugate heat transfer analysis, or would use this here, for example, as a porous region. Okay, so I can also switch here again to the color, and I can also color here my model by region, and then it looks like this. So this is a model that I need here for my CFD analysis, and then I can go to meshing. In the meshing tab, I have here a number of options that I can use here as attributes. I can apply these attributes step by step to the model, but the faster way to work here is that I apply a template here for typical analysis. So in this case, we have some predefined templates for CFD, and we recommend, for example, to use here the CFD medium size template with hex core elements and boundary layers. So this applies me a certain set of attributes, here I can, of course, modify and change them. Here I have here, for example, a typical mesh size in my model. This is applied to my complete model. I can see here, for example, that I use here a curvature refinement, and where I can here add values, and also I use here a boundary layer. And here at the moment, I use a boundary layer in all regions. And with a certain definition of the boundary layer, for example, a gradient factor of 0.5, which is a quite fast gradient, and 3 layers. But of course, I have here a quite large number of defining different boundary layers. For example, I can use here a specific first layer thickness, but as a general template, we don't know, for example, which first layer thickness we would like to apply, and therefore we use typically this kind of boundary layer as a general boundary layer in the model. Then I see also here an attribute which is called no boundary layer, and these are my interfaces here, where I don't want to have a boundary layer. For example, these are the faces which are here between the parts. Okay, and when I go here to generate mesh and generate here mesh, this is quite fast, and I can see here how the mesh looks like. And investigate the mesh in detail. So the mesh looks like this. I have typically a hex core meshing with boundary layer. The boundary layer is going through the different regions and so on. So based on this, I can improve my mesh settings here, for example. If I would like to use, for example, here an extrude in this region, I can define this here, extrusion meshing. and use here, for example, 10 layers. I go here to mixed elements, and I also can use here a gradient and so on. And also I can, for example, pick this face and also use an extrusion meshing. And also in this case, the destination face is found automatically here. I can use here also 25 layers in this case, mixed elements, apply, close. And then I get, when I go here to generate mesh, the mesh looks like this. In this case, I have the extrusions. Here I have the extrusions. And this is a mesh I can also use here in my analysis very well. So in the next step, I can define my OpenFOAM settings. I can go here, define a new OpenFOAM case. I go to new case, say here OF1, for example, and can apply a template here. Here we have this list of templates for the different solvers that we support. And in this case, I would like to do analysis with simpleFoam. I apply here a template for simpleFoam. And here the attributes are added to my case. I can typically what we do here is that we have some attributes where we have here these kind of capital letters. And these are the attributes where we definitely have to do some changes here. So here in this general models, I have to check the version I would like to use. Here I can easily select the OpenFOAM version I would like to use here by selecting this in the list. So here I would like to do this analysis first here with BlueCFD, which is OpenFOAM 12 based, and also I can change here the turbulence models and so on. Then as I used here simpleFoam, I get here the transport properties where I only have to define one parameter. If I use here, for example, row simpleFoam, then of course I get here another entry where I can define a perfect gas or something else. The control dictionary is also designed here for steady state applications where I do 1,000 iterations and write results after every 250 iterations. Finite volume schemes, I use very stable schemes here at the beginning because I can also change them later in RunGui. And here, for example, always upwind schemes, but I can also change the schemes directly if I would like here to start here with more accurate schemes in this case. In finite volume solutions, we can also define our matrix solver settings here directly in the relaxation factor, but typically we work here with a lot of defaults, so the user don't have to define anything here. And in pre-run post options, I find here these capital letters again. I can define here how much cores I would like to use here in the simulation. And as I run here this case on my small notebooks, I think 2 cores are fine. So then I have here initialization options, and here on the inlet, I have to define here. I definitely have to define something. Here I tick the face and add the face here to my model association. So this should be the inlet. And then, of course, I have to define here an inlet value. For example, in this case, a face normal velocity. But of course, I have here many other options to define here an inlet velocity in this case. Okay, then I pick these outlet faces and I add them completely here to my outlet condition, which is already here predefined, where we use an inlet outlet typically. But of course, if I have other boundary conditions, I could also add them here as well and assign them to the specific faces. Okay, then everything is defined so far. I defined the version, the material properties I checked, then the inlet and outlet conditions, and then I can export this case here and write this into a new directory. And I go here to export analysis. In my mesh case, I say ignore here, and then I write this here to case 1 and export the case. So if I would like to run this case here on another system, of course, I can take the complete directory and move this to another system as well. But here at the moment, I would like to run this case here directly on Windows with the BlueCFD. And what we also do here in our settings is that we check here the case and if everything is defined correctly. And here you see that no critical errors have occurred during the export. So everything should be defined well. And then I can go here to RunGui and run the case here with BlueCFD 24. Okay, then I go here to my directory. I go here to import the input file for my case. I go here to data webinar case 1. And here we export a bunch of files with all these settings. And here we have certain scripts. And these scripts generates me the OpenFOAM case. Then I have my typical case structure with a 0 directory, constant, and system. And then I can go here to form solve and solve the case. Okay, I see now the case is running here. And as soon as the case is running, also we start here with the monitoring of the case. We can look at the residuals. We see here the inflow pressure that we have here. We can define in CastNet different monitors that we would like to use here, and then we can also monitor, for example, temperatures at the outlet or pressure at the inlet and so on. We have a lot of functionality to modify the case. We can, for example, modify the schemes that we have here. We can modify here our setting in our control dictionary or in finely volume solution. We can do this directly here in the GUI or also in the post-processing. As I said, we can later, when we have the case, for example, we can estimate the Y+ values and so on. Also, while the case is running here, I can I can also look here during the running of the case, also at the results. I can start here ParaView directly, but it will take a little bit of time until I have my first results. At the moment, we are at iteration 120 approximately, and our first results will be at 250. But so I can go here to the decomposed case, click here on apply, but I don't have results yet. But as soon as I have them, I can look at the results during the simulation. Yes, so we have also many other functionality here in RunGui. We have here additional mesh utilities like check mesh. We can do manipulations on the mesh. We can extend transform points, for example, rotating the mesh or make it smaller. We can refine the wall layer and so on. The post-processing side is something that I already showed here, where we can also translate the results here into the VTK format or estimate additional values here for OpenFOAM. So after 200 iterations, I should have my first results here, and then I can also look at them. So I can see it in the post-processors that are already there. Okay, then I can go here to ParaView. I can refresh ParaView and go, for example, to the results that I have here, for example, after 250 iterations. So, of course, the pressure and the velocity are not converged yet, but during the simulation, I can already look at the results and do some and look at them also here in ParaView. I can do here, for example, slices already. And then if I see that the Okay, then the velocity field still develops here. Okay, I don't want to wait until this case is complete because I would like to demonstrate you how to use this, how to run cases here with conjugate heat transfer as well. So I kill this case here. And go back to CastNet to set up a case for conjugate heat transfer. So I can do this still with this model. For this, I have to do some manipulations with the geometry. I would like, for example, to add a solid. At the moment, I can't do this because this is blocked as I have some active mesh tabs here open. I click here on OK, and then I close here the meshing tab. And then I can go here to modeling, and then the modeling is active here. And then I can, for example, add a part. And I can add here, for example, a heating component. This is my heat element. I add this here to my geometry. So when I look at this part here, then this part is not really connected to my geometry. The tubes are going completely through the part. And also here, I have two faces. So I have to boolean this part with my model. I click apply, and then the geometry is split. And then I can go here directly to meshing again. So, and still all the extrude sections and other sections that I defined here are available. And then when I look here, for example, at the model, I can use here a clipping plane. I click here apply, and I see, for example, that I should use a better slide clip here. Clips with a solid. So at the moment, my solid is not in the, my solid regions are not in the boundary layer definitions. This is fine. So for this, I see here that the boundary layer is going around these solid regions, which is perfect for me because I don't need a boundary layer in a solid model. I only need this on the fluid side, and I get here very good resolution for the heat transfer in my solid. Okay, then I can go here to my analysis settings. And as the settings for conjugate heat transfer are quite different in comparison to a simpleFOAM, it does not make sense to change here my simpleFOAM case for a conjugate heat transfer. So the easier way is that I define here a new analysis case. I call this here CHT and apply a template. For conjugate heat transfer multi-region simpleFOAM. So, and in this template, I have here automatically two regions. I have here a solid, a fluid region I have to assign, and here I have to pick all my parts or my regions that belong to the fluid regions, which are these. Then I click Ctrl H, I hide these regions, and then remaining are the solid regions. And here I can pick here the solid regions and add them to my solid definitions. So when you already work with OpenFOAM and conjugate heat transfer, you probably know that the settings are quite there are a lot of settings available here for OpenFOAM. So you can define, for example, in each region that you would like to use here, or if you have multiple fluid regions, you can define your different turbulence models in the different regions or different material properties in the different regions. We would like to simplify this. For example, if you only have two regions, then we have one typical fluid region here. But of course, if you have more regions, you can add more regions here as well. This is quite easy. But here we have, for example, fluid regions with standard properties with default finite volume schemes, finite volume solutions. But if you would like to use specific properties in specific regions, you can also assign them here to the specific regions. Also, the materials that we use here are the material for air, for example, in the fluid regions. And on the solid side, we have here the properties, for example, for the solid regions, which is alumina in this case. And also, if you have more solid regions, you can easily generate them by defining an additional material property for solid region and an attribute for a fluid, a solid section. Again, we have to go here to these attributes where we have here these capital letters. We already assigned here the regions to our models. Then again, here we have to select the versions that we would like to use here. Here in this case, I would like to run this with the ESI version, also on Windows here. I say here apply close. Material properties I already showed. And then, of course, again, I have to define your boundary conditions here for my case. I have again here the boundary conditions here at the inlet. I can pick a face here at the inlet, assign this face here to my attribute, define here the value for the boundary condition, here 0.1 here. And also here I have also the option to define a temperature here at the inlet, say this is fine. And also here I have to define here, pick these faces again and use them here in the outlet. I say apply close. So of course, I would like to have here a certain heating effect. So I can pick, for example, this face here. I can define here a wall, and then I call this here heater. I set the thermal settings here and use here, for example, a constant temperature of 350 degrees. And this is my heater here from the solid. So then I can check once more the model. It's fine. I think I defined here the boundary conditions, the heater as well, and I used here the version. And then I can go again here to my model and export the analysis. Here I have to select the case. I have to select the conjugate heat transfer case. I call this here CHT. And export the case. So as I said, I would like to run this case now with the ESI version of OpenFOAM. I can easily switch and run with the OpenFOAM version I would like to use here also on Windows. And then I get here a new window of RunGui where another OpenFOAM version is sourced. So let me see if the Explorer. Okay, also I see here the export is fine. And also in my new RunGui window, I see here that OpenFOAM 2406 is used here. I go here to my directory here where I exported the case. Okay, and then again, I execute this prescript here, and this generates me here the case structure for my conjugate heat transfer case with all the subdirectories that I would like to use here. And in the next step, I again go to Foam Solve to run the case. So when I look here, for example, in the system directories, I have here the subdirectories for the fluid regions and the solid regions. And also I have the same here, for example, in the zero directory and so on. And then I can go here to Foam Solve and run the case here. Again, I run this case here in parallel with two processors. And yeah, and the case is running. And the plotting tab, I can also see progress of my simulation. We see here also the outlet temperature and the inflow pressure and so on. So this can be defined in CastNet in the specific boundary condition that I have here. Yes, again, here this case is running, and yeah, again, it will take around 250 iterations until I have here my first results. And yeah, and everything runs here in parallel. Again, here I could also start ParaView again and launch the ParaView reader to look at the results. I think the setup has been clear, and I hope it has been clear. And yeah, I think I can also stop this case here. I think we don't have to wait until we get here results for this case. Okay, so these are the two cases I would like to demonstrate. And I think if you already work with conjugate heat transfer analysis, I hope it became a little bit clearer that the case setup is really much very fast here, and we can easily assign here different regions to our model. Okay, then I go back here to my presentation. So what we think where CastNet might be extremely useful is, or what are outstanding features of CastNet is that we can support here different OpenFOAM versions and on different operation systems. So you can, for example, export the case for a Linux machine. You can run the case first on a Windows machine, and you are not fixed, for example, to use, for example, an easy ESI version or a version from the OpenFOAM Foundation from Henry Weller, and you can always pick the best version for your specific case. So, for example, in the last Foundation versions, settings for rotating applications became very strong. You can do, for example, sliding mesh application with the Foundation versions, or on the other side, if you would like to do if you would like to use the isoid vector method in the ESI versions, you can easily set up this here for the ESI versions. On the other side, you can easily export this for different versions and also switch, for example, from a small machine, for example, to a cluster or to the cloud as well. Also, we think that this template approach makes the setup for OpenFOAM much easier. So you don't have to take care, for example, for the different definitions, if you need absolute definitions for your solver, or if you would, or which properties you need to define, if you need transport properties or thermophysical properties and so on. Also, we think it's quite an advantage, or we see this in our engineering project, to have different meshing options available. For example, to have the hybrid meshing in specific applications. On other sides, snappy hex mesh is also very powerful in certain cases. And also, we on our side switch sometimes between the hybrid meshing and also snappy hex mesh. Also, what is also quite powerful in CastNet is that we have here these kind of multi-region applications where you can easily use a CAD model and transfer this into regions, for example, for conjugate heat transfer analysis, or multiple reference frame, porous regions, sources that you would like to define in certain regions, and so on. Also, the generation of this non-manifold model based on a CAD assembly is also a powerful functionality that we also get here from the metrics in the setup for CFD cases. Finally, we have here these coupling options. I didn't show this into detail because this would take a little bit longer here to set up also a case for Calculix as well. But you have the option, for example, to map results from OpenFOAM to Calculix, for example, pressure on the wall, and use this as boundary conditions, or if you would like to use a temperature field from OpenFOAM and use this in Calculix for a structural analysis for thermal stresses. Also, Precise allows some powerful FSI applications, and there's also a very powerful coupling here available between OpenFOAM, Calculix, and Precise. What I also didn't show here directly is our automation options here. What I showed here as template approach is also just the surface of what we have here as options available. We can use this approach to conduct very easily and powerful parametric studies with the Python scripting. And if you're interested in this, we can do easily a separated session where I demonstrate this functionality. Okay, so with this, I would like to conclude my official part of this webinar. And I thank you very much for your attention. And I think Martin already, as I see, he already replied a lot of the questions that you already have. But if you have still further questions which we don't cover yet, I'm still here to answer them here, or we come back to you if you would like to see special features or something else in our GUI. So yes, thank you very much, and have a good day.